Okay, cool. Yeah.
Might make food run during your talk. Oh well, maybe I'll make it after your talk. Make the food run after.
No, there is just no good talk to skip. I took a big breakfast and I just go eat something like at 3 after all the talk, just before the action.
I just need to go anyway. Okay, can everyone please settle down and then we can get started on Sylvain's talk. So, like people in just either sit down or leave.
Okay, so
thank you very much.
Yeah, thanks. Good morning. Thank you for being here. So, for a few words about me, in case you don't know me, I'm Sylvain Munaut. Speak up, okay? My name is Sylvain Munaut. I'm an engineer, and I'm generally interested in everything that's low level. And recently, I got interested in everything that's radio and communication protocol and stuff like that. And I work inside the Osmocom project, and that's what I'm going to talk about today. So, what is Osmocom? So, Osmocom stands for Open Source Mobile Communications, and basically what it is, it's a sort of an umbrella project. It's a collection of sub-projects that are all related to the open source and free software implementation of various communication protocols. It all started like in 2010 with OpenBSC, and we needed to create other projects. And we needed a good naming scheme, and so we came up with Osmocom and the Osmo prefix that we know often use. It was really centered around GSM at the very beginning because it's part of a GSM project, but nowadays we have many more protocols and stuff, things that have nothing to do with GSM, and a growing number of them is now involving software-defined radio because it's just a very easy way to implement new protocols without having to buy expensive hardware. And so today what I'm going to do is I'm going to try to give you a very short introduction to all projects that are related to SDR. We have quite a number of them, so it's going to be really a short introduction to each project, hopefully, so you can see what interests you and dig a little deeper on our website or other talks that have been done on those projects. Most of the projects I'm going to present have had dedicated talks just to each of them in the past. So, yeah, it's a short introduction. Obviously, I'm not actively involved in all of these. A few of these I'm the maintainer of, but some other I've never even used. So I just try to ask the author what to say about them. So I classified them in 3 main categories. The first one deals with everything that's interface with the external world, what I call radio front end. Another category is like signal browsing, so you can visualize signals or like standalone SDR application. And finally, really just implementation of a given protocol and how to deal with that specific protocols. So, rtl-sdr is probably the most well-known of our project because it really boomed like in mid-2012 or something like that when a kernel developer essentially discovered that some of those dvb-t dongles that you could buy for very cheap had some kind of SDR mode where you can get raw IQ samples. At that point, an Osmocom developer basically created a library so that you could actually use that SDR mode and integrate it into your own project, and thus was born the rtl-sdr project and the lib-rtl-sdr that corresponds to that. So those dvb-t dongles, they're really cheap because they're mass manufactured and they're meant to receive TV. But you have kind of a debug mode where you can use the raw hardware and get the IQ sample, and it has everything that a classic 0IF or low IF direct conversion receiver has. So basically you have the antenna, an amplifier, some kind of filtering, a mixer down to baseband where it's sampled into IQ complex that you can get and feed to whatever algorithm you want. On the other hand, you kind of get what you pay for, right? I mean, in absolute terms, the RF performance is terrible. there is spurs all over the place. The sensitivity isn't the best. You only get like 2.4 megasamples per second, and even then you're not always sure that you don't have discontinuities in the stream and stuff like that. But it's a great way to get started for SDR with basically no investment. So if you don't have one, I definitely recommend that you get one, because it's also so small you can just have it all the time with you, right? It takes basically no place. And although the performance isn't good, it's still very much sufficient for a lot of stuff. I mean, pretty much all the protocols we've managed to implement them using this dongle, because you know, as long as you're not working, you're really at the edge of performance and trying to dig out signals out of the noise, you're gonna have sufficient signal-to-noise ratio, and with all the error corrector codes and stuff like that, you'll manage to recover the signal without much trouble. So another project which is less known is the gr-SDR, and basically, I mean, the first project was meant for the Realtek chip, and Mirix, another manufacturer, has basically the same feature in their chip, and so an equivalent library was created. It's more of a proof of concept right now, because even though the hardware itself has better spec on paper, there are some serious downsides. First, they're kind of hard to get. I mean, back when I bought one of them to test, I had to go through you know, a Japanese mail forwarder, because there was no way to order them here in Europe. They're more expensive, and the biggest downside of all is the actual tuner, so that you can tune to different frequency all over the frequency range. They have different antenna input depending on which band you're in, and most of the dongle you can buy, only one of this input is connected to an antenna connector. All the others are just connected to ground, and so you have a very small frequency range that you can actually use, even though the hardware can do better. And with all those very small QFN chip, it's nearly impossible to go and solder another antenna. So if another manufacturer came out with, you know, different antenna inputs or stuff like that, it would probably be worth investigating. But so far, if you have a choice, I definitely recommend that you get a rtl-sdr instead. Now, of course, these are just raw libraries, and we wanted to use that in, well, GNURadio, of course. And so Dimitri here started working on gr-osmosdr. And gr-osmosdr is essentially a hardware abstraction block. It started only as a source so that you can receive, but now you have also a sink so that you can transmit with hardware that supports it. And what it allows you is to essentially create a GNURadio application. You just use that source or that sync block, and whatever hardware the user has, it's going to work for it. It has a large number of backends nowadays. I mean, you can read from files that you previously saved. You can use the FunCube dongle, everything that uses UHD, that means all the Etus USAP, you can use them with, and also the UMTRX. It has support for some osmo-SDR, which is some Osmocom actual hardware, but it's not actually available currently. You can support the rtl-sdr, you can support the mir-SDR, you can support the ACRF, the Blade RF, and the upcoming AirSpy, and some RF space receiver that are targeted at AM radio, I think. So, and all those boards, the support for all those boards has been made possible by all the hardware vendors that have been kind enough to provide hardware so that we can develop and test, which is pretty important, and so a big thanks to them. That block is now used in a wide variety of projects. I think maybe the most user-friendly one is GQRX, and also the block. So for those that don't know, GQRX is like a generic SDR application where you can listen to FM signal or AM signal and stuff like that, and underneath it uses GNURadio, and among which it uses the gr-osmosdr source to support all those hardware as inputs. And if you're creating a GNURadio application, I definitely recommend that you use gr-osmosdr block as a source. It's, I mean, kind of depends on your application. If your application has very specific requirements that are pretty tied to the hardware that you're using, of course it's not going to work, but most of them are not that tied to the hardware. They just want samples, basically, and this would work great. the blocks actually comes with some sample application, so that once you install it, you can actually directly start using it. And it's basically Osmocom FFT, which is a quick and dirty spectrum analyzer. You launch it and you can just browse the spectrum using the default GNURadio instrumentation stuff. And you have a SIGGEN, which is basically the equivalent in the other direction, where you can easily like generate a tune or a modulated signal or even actually GSM bursts, just to test your hardware quickly. So now we kind of move on to visualization, and there's two main applications. One is called Strangelove, and the other is called Phosphor. This was what Strangelove looks like, and you'll see that Phosphor looks very similar, and there's a very good reason for that. So what Strangelove is a standalone application. It doesn't rely on GNURadio. It's kind of an equivalent to GQRX or to SDR Sharp or HD-SDR or that kind of application where you can tune to a signal and just listen to it. One of its main features is obviously its display, which is very nice, but in the case of Strangelove, it's also very CPU intensive, which means it was originally targeted at hardware that could provide only a few megasamples of like sample rate, like the osmo-dr or the rtl-sdr dongles. It's been extended to actually be able to use the gr-osmosdr. You can, if you have GNURadio and gr-osmosdr installed, you can just use them, and then Strangelove will actually use GNURadio as a sample source. But you can also compile gr-osmosdr in some special standalone mode for this application in particular. Another of its interesting feature is the ability to select a piece of spectrum, channelize it, and send it to an external application, so that you can use this application to bookmark frequency and channels and tune to them, select just the channel you want, and then send that to an external application that will then do the processing, like for example VSD or some other application that expect pre-channelized data at their input. So this is Phosphor, and as you can see, the kind of display is very similar, and that happened because of the performance issue of Strangelove. I don't have the latest laptop, and you know, when you get on my like Core 2 Duo CPU, I can maybe process like 2 megahertz of spectrum using Strangelove, and that's just not enough when you have SDR nowadays that provides, you know, like Blade RF, it's like 40 megahertz of spectrum, the P200 is like 56, and I know you get, you know, people with 200 megahertz and all, so yeah, processing everything on the CPU just doesn't cut it. So I wrote a Phosphor, which is essentially a complete rewrite of the display part of Strangelove, but using GPU processing, and also designed as a GNURadio block, because that's the other thing, is I wanted to be able to use it in GNURadio. And so this is essentially what Phosphor is. It's GPU accelerated, which means, well, you need a GPU, and you need a GPU with good enough drivers that they support OpenCL, and even more what's called OpenCL, OpenGL interop, which means the cooperation and sharing of buffers between the actual rendering part and the computing part. On OS 6, it means pretty much all recent hardware should be supported. Everything above the HD 4000. Actually, even the HD 4000, but only on macOS 10.9. If you're on Linux, that pretty much means only ATI and NVIDIA's. There is some effort to support the Intel with the so-called Benia project. I don't know its state, I just know that it doesn't support all the features that are required so far. But hopefully they'll get there, and that would be really great. So I'm hoping to be able to backport that display also in Strangelove, and it's also integrated in gr-osmosdr, which means if you launch the Osmocom FFT demo application with the you know, uppercase F option, then instead of using the default WX widget, you'll use the the phosphor rendering, which looks much nicer. So I'd like to take also some time to explain exactly what is in that display, because it looks good, but it's also useful, right? It has some really interesting properties. So at its core, obviously, it's basically an FFT. It's real-time spectrum. One particularity is that every single input sample will go through at least one FFT. In the future, we're actually hoping that it will go through several FFT, and it's important because if you have very short transient burst, like interference or whatever that's lasts for a very short time, if you take the approach that's used by the default sync in GNURadio, they only take like 1,000 sample, like 10 times per second. But if you have bursts that last for less than that, you might never see them. In the case also of phosphor and Snezlov, you will definitely see them because every single sample is processed. And so they will definitely appear in the waterfall, the spectrogram display. Compared to some other waterfall, like you saw the waterfall in Income talk, the waterfall in here is much faster, in the sense that it displays like only a few hundred milliseconds of past samples, and that means when you have hopping protocols that change frequency very fast, or when you have things like frequency block allocation LTE, like for example in the screenshot here, yeah. So this is a LTE signal for those of you who haven't recognized it, and you can clearly see like the pilot, the periodic pilots here, and the block allocation and stuff like that, and you can see that well enough that you wouldn't see in the default things. And of course, it's more than the waterfall, it also displays the live spectrum. It's averaged, and again, since we have so many FFT, so many spectra coming back, we can actually do pretty long averaging, which means it flattens out the noise. But I mean, even if you average 1,000 spectra at 1,000 points per spectra, and you have 40,000 megasamples per second, your time constant is still only like 25 milliseconds, which means you've got a very flat noise floor, but you still have very much a lot of responsiveness when new signals appear and stuff like that. You don't actually see the average. And of course, the main feature is the histogram, which is that kind of display that you get on high-end spectrum analyzer, which shows a statistical distribution of the signal. And if you go back to the screenshot, you can, for example, here clearly see that. You can use this. Yeah, you can clearly see that. So this is the noise, and you can see kind of the spread of it. And you can see that there is two main power levels for the signal, and in the middle there's pretty much nothing, and that's essentially a reflection that either on the infinite area there is nothing between the gaps, or you have transmission of blocks and that kind of things. So that's pretty much it for signal browsing and display. And I'm gonna move on to a real implementation of protocols. So the first one I'm going to talk about is called GMR, and GMR stands for Geo Mobile Radio, and Geo stands for Geosynchronous Earth Orbit, and it's essentially a satellite communication protocol. It's heavily inspired by GSM. Pretty much everything above layer 3 is going to be GSM, and everything below has just been modified enough to work on high latency links and stuff like that, and to save power, because obviously when you're in a satellite you don't want to waste power transmitting a constant beacon for no reason, and that kind of stuff. Its main user is Turaya, which is a big like satphone provider in Asia. I think there are some usage of GMR protocol in the US, but not really targeted at consumer, more like machine to machine or stuff like that. However, I've never had actually the chance to search for any of those. The current implementation, sorry, is pretty much it has a complete PHY in the sense, well, complete in the sense it implements all the channel coding and stuff like that, and TDMA patterns, both for TX and for RX. The actual SDR part currently is perception only, but transmitting should actually be fairly easy to implement. I mean, it's just QPSK. It's much easier to modulate a signal than trying to recover it. So it should go fairly easy to implement. It uses GNURadio to channelize it. It's not directly linked to GNURadio. Basically, it compiles independently, but it expects pre-channelized data. And I mean, there was no point for us to just re-implement channelizer when they exist in GNURadio and so on. So what we essentially do is we use a GNURadio application that will take a chunk of spectrum, go through a resampler, then a polyphase channelizer block, and ship that to a bunch of named pipes on Linux. And each of those pipes actually represent one channel, and those are used by the actual osmo-gmr application that will take the samples, demodulate the search for broadcast channels when it finds some, actually follow them, decode the packets, take those packets, forward them to Wireshark, and when it sees its channel being assigned, it will actually follow those channels. If you provided the proper decryption key, we'll actually decrypt them, take the voice packets, save them on disk, and that kind of stuff. So as I said, we forward them to Wireshark, and there's a good reason for that, is that we implemented a Wireshark dissector, which means you can actually inspect the different packets and what they contain in Wireshark pretty easily. And we implemented both the GMR specific packets, and as I said, it's heavily based on GSM, which means pretty much every layer 3 message there was already a dissector in Wireshark that had been written by people, I don't know who, but somebody wrote them sometime, and we're very grateful that they did. And so we just reused that. As part of the project, we also the cipher itself was reverse engineered in parallel pretty much by us and by the University of Bochum in Germany, and they published their result, and we actually validated them with real on-air data. They presented an attack on the cipher, which is really slow. We kind of developed our own, which is really fast. I mean, to give you an idea of the level of security in satphones, it takes less than 1 second to recover the crypto key. Even when you're decoding your own call, it's just faster to just crack the key than reading it. We had another problem is the voice codec. The voice codec is a proprietary AMB variant, and if there are some AM in the room, you might know D-star and all the kind of protocol that they all use AMB variant, but they're different enough from each other that you can't actually reuse the decoder. And last December, we actually reverse engineered completely the voice codec, and we now have a clean C implementation of the voice decoder for the codec. And what we're looking now for the next step in the project is we're looking at GMPRS, which is essentially the internet over the satellite connection, which is completely different protocols and stuff. Maybe adding some TX support so that we can actually, start like a satphone base station on Earth. Because for GSM you can experiment and buy old hardware. They just don't sell old satellites. Yeah, shipping would be a bitch. And we're looking into better GNURadio integration, essentially, so that everything can happen inside GNURadio, and especially for GMPRS, the current approach we're taking with the polyphase channelizer has some limitation. That's what we're looking into oh yeah, something I forgot. We actually have a map on the project. We're trying to collect as much GMR data as possible. So if you're interested, definitely collect some data, send them to us, so that we can collect more information about the broadcast channels. And we're trying to get more data, especially in Asia. And also, if you're in the US, I'm pretty sure there's some GMR signal there, but I don't know where, so you have to look. And since it's satellite, you pretty much need a directional antenna, so yeah. Another project we created is Tetra, osmo-tetra. So Tetra stands for terrestrial trunk radio, and it's a digital, trunk radio system that's targeted at government agency, emergency services, and that kind of stuff. It's widely used in Europe in general. I don't know about the rest of the world exactly. I know it's used here in Belgium. If you look around 390 megahertz, you'll find what's called AirStreet here in Belgium, which is the Tetra network used by police and stuff like that. It's encrypted since we published osmo-tetra, pretty much. When we started it wasn't, and then we kind of tweeted that oh my god, it's not encrypted, and like 6 months later they encrypted it. If you go through Brussels airport, you can look at around 410 megahertz. There's an unencrypted Tetra network there, just for the airport people basically, and they all have this Motorola radio. So osmo-tetra is pretty much the same thing. You have a Phi and Mac implementation as a separate application. We use GNURadio for both for channelization and the actual demodulation. We actually reuse the demodulator from another GNURadio project from UP25 because it's for FSK and for FSK demodulator. Again, we use named pipe between applications to pass data around. We have a Wireshark dissector that was actually kind of generated by us, but not. We didn't do most of the work. Some university in China somehow described the entire Tetra protocol in ASN1, and then from ASN1 we could generate automatically a packet dissector from Wireshark. So yeah, we're very grateful that they wrote that and that they let us use it. That was really nice, because if you haven't written Wireshark dissector, it's really boring work. I mean, it's basically describing every little field with a help text and a name, and oh my god. We have voice support. In this case, the codec is actually public. There's a reference implementation. It's not, it's not free software. The license is not. I can't take it and redistribute it. But we have something that essentially downloads it, patches, compiles it. It's not in master yet, but there'll hopefully be some work done on it to, make it more user-friendly. And the last project is UP25. So UP25 is actually a project that didn't start as an Osmocom project, and it kind of joined us afterwards, and now we kind of host them. I've never used it myself, mostly because UP25 is kind of the equivalent of Tetra, but for other part of the world, mainly in the US and Australia and Canada. So if you're from there, you should definitely check it out, because you most likely have some P25 radio signal there. It's entirely based on GNURadio, and it's pretty complete. I mean, they have everything, from demodulator to the complete protocol stack to implementation of the codec, and they also implemented Wireshark packet dissection and all the crypto stuff. They've recently updated it to, they've switched from SVN to Git, and at the same time they've kind of made some architectural changes, including changes to the latest GR 3.7 API. They also use some of the more advanced feature of gr-osmosdr for tuning and stuff like that. So yeah, it's definitely definitely a great project, and definitely a good example to follow if you, yeah. So that's pretty much it. I'd like to, well, first thank you for your attention, and thanks every developer of Osmocom that actually works on those projects, and in general in all the SDR projects. We need more people working on this stuff to hopefully both make them more advanced and also make them more accessible to a wider audience. And there's really a wide variety of tasks to be done, and not only hardcore DSP stuff. So yeah. Yeah, if you have any questions. For
the visualization part.
Yes.
Is there a way to actually easy visualize small packets which come up randomly? The problem if you do water graph, you only have packets. Sometimes either it's slow, and then you have a packet size of that where you don't see the detail, or it's fast, and then by the time you actually do something, it's gone. Is there a way to trigger?
No, there is no trigger yet, but I was talking about doing like things like spectrum-based triggering and that kind of stuff. But it's really advanced kind of stuff that I definitely would like that, because as you said, there is no good compromise. Either you just don't see them, or they just appear as like a line. And currently, I'm planning on adding like a pose mode, so that you can at least pose the spectrum and inspect it in closer look. But you know, automatic triggering would definitely be good, but it's not there actually, currently.
Another question for the not really Osmo, but for the hardware kind.
Yeah.
Do you support something that can transmit, say, 20 watts?
I mean, not directly. I don't.
2 megabits of second on UHF or half a megabit.
Yeah, I mean, you can do it, but usually it's not really our problem, in the sense that you will connect to SDR, and then that SDR will transmit a signal. If you want to transmit 20 watts, you're probably going to want to filter that signal at the output of the SDR, then go through possibly a preamplifier, then another filter, then finally the power amplifier. But most of the SDR I know don't have 20 watt power transistor on them. Yeah,
there is one. The HB-SDR. It has a PA of 20 watts.
Right, really?
Yeah, the HB-SDR that's an amateur radio project, basically. So yeah, they're interested in that.
Ah, we did one funny. I don't.
Well, real stuff costs money.
Yes. He says that it's free open source.
The question, is your project related to OpenBTS in some sense?
Not that much actually. OpenBTS, there is some relation, in the sense that so OpenBTS is mainly two applications. I'd say it's one implements like layer 2, layer 3 and stuff, and one is like the actual radio modem part. And the radio modem part has kind of been split off. It's maintained by Thomas Tzu, which I saw, but I don't know if he's here. Okay, yeah, he's there in the back, and he's maintaining the actual SDR part of this. And I mean, although we know this on our Git, and this is what he maintains. I just didn't include it here because it's still mainly the work of the OpenBTS guys who did it originally. Yes?
What is currently known about the tetra encryption?
Nothing. I mean, really not that much. The spec don't specify it. So, and even it's very hard to test because it's very hard to get actual tetra hardware that both supports encryption and that you can easily play with. I mean, we have some tetra radio. Some of them actually support the encryption, but we have absolutely no way of loading encryption keys in them. We have no idea how it works because it's. I mean, you just can't get the documentation. It's usually done at the factory or provisioned through a big system, and so basically, we just know that we don't really know much, and certainly not enough to do anything about it.
Okay, because I know the satphones were like they had their firmware reverse engineered because it was freely available on the internet.
Yes, and we can do that for the radio too. The problem is in Tetra there is. It's not as. I mean, in the satphone case, in the spec you basically add a nice block schematic, and everything was known except for the actual encryption algorithm, right? But its input and its output were all specified and stuff. In Tetra, you have the encryption algorithm that is secret. Then you have the key derivation algorithm that are secret, and there's a bunch of them that are secret. And even if you reverse engineer the stuff, you have no idea what is what. And without the ability to actually test on real hardware to confirm that what you found is actually the real algorithm, and you can actually decrypt the bits. You're just basically doing work blind. And so if any of you has any contact in Tetra that can provide us like a radio that can transmit with a known key, that'd be really helpful. Yeah.
Two quick questions about Tetra.
Yeah.
One is, do you know if you use Tetra as simply a packet data radio?
Yeah.
Are there any patents that apply?
I have no idea. Honestly, I just gave up on patents. Sorry?
When Google bought Motorola, do you know if they got the patents for Tetra?
I have no idea. Sorry. As I said, a lot of stuff are patented and yeah. Yeah. Okay. Yeah. I figured pretty much all of them have patents, and if I stopped implementing stuff because they're patented, just. Okay.
The second question is, do you know if there is some sort of EU directive deregulating Tetra in the future for ISM?
Oh, so that you can transmit Tetra in AM bands.
Because it's very strictly regulated right now.
Yes, yes. I mean, no, I have no idea. I think. I mean, when you buy like Tetra radio, you can buy them for different bands. I don't know if any of them actually overlaps with. I mean, one of them is like near. One of the Tetra band is near 433, right? But I don't know if it's. I mean, just because the frequency is right doesn't mean you actually have the right to transmit on it. So, yeah. Legislation and me. It's not, okay. Yeah, sure. Yeah. In green.
One question, you mentioned that you're using the GPU inside GNURadio and gr-fosphor for
Yes.
the FFT.
Yeah.
And how much work would it be to adapt your code that the GPU is doing something entirely different? So you have much with the code processor.
It wouldn't be that much work, but it really. I mean, okay. So currently, what I'm doing is I'm taking the samples, I ship them to the GPU, then I never see them again. Because transferring data from the main memory to the GPU takes a lot of time. I mean, for the high-end graphic cards that can process like 200 megahertz of spectrum, copying the data is like 90% of the execution of the time, right? And so I'm not gonna copy like a big chunk of data, then do an FFT and then copy them back. FFTW is just faster. If you are doing a lot of stuff, then it would be worth it. But yeah.
If I can jump in, we do have a project called gr-GPU. You can find it on GitHub. That is basically what you're asking for. And it basically has like a block that moves data to the device memory. Then you write your GNURadio blocks in GPU code, which was CUDA. Now they support OpenCL. And then you have a block that brings it back from device to host memory. It's not perfect. There's still a ways to go, but there is support.
Okay. Yeah, sure.
Do you have plans for LTE and LTE safety, which is the next gen network?
Plans? Not exactly. I mean, we usually don't plan that much. We just, oh, that looks interesting, we're going to look at it. But most of the time, that kind of implies that we have hardware or something to look at beside the spec, because just reading specification is also not that interesting, and so we like, at least I like to look at signals and the spec in parallel, and so until I don't actually have LTE in Belgium, so yeah. Sure.
Yeah. When we talk about digital radio, software defined or other software, you mentioned here AMBE and DSTAR codecs. Yeah.
Yes.
Close standard, close codecs. But we have here in Europe digital mobile radio.
Yes.
This open standard is approved, is having all the regulatory and the technical setup, is a goldmine for software developers. Have you considered, did you look to the European chart?
Most of the time I mean, when I started like the GMR project, I thought there was a reference codec implementation in the spec, because every other protocol I did before, there was a reference codec. And so it's only when I extracted and took the voice packets, and then, okay, I go to the GMR site and I look for the reference codec and just can't find it, and what the fuck? And so that's only at that time that I realized that I needed to actually reverse engineer the codec. Yeah, but if I had the choice, I'd take open codecs, of course. But since I'm implementing existing protocols, I take whatever they chose in the spec, right? Yes?
So I was wondering, is there anything else out there for DMR? So I've used DST before, but it specs like OSS, which is great these days.
I've never really played with DMR. I just know there is a gr-dsd block. I tried it a couple of days ago, and it works. I tried it for D-Star, and it worked. But yeah, I don't have any DMR radio to try, so sorry. Okay, I think we probably over time already. So thank you. Yeah, I can take my stick.
Yeah, just yank it.
Thanks a lot. You're welcome. Bring more chocolate. Chocolate? Don't worry. Don't worry when you yell. Starting right now.
Which we have both. We've seen evidence in the barrels never seen it, but it's so big.
Can you get guard? Non è più amatoriale.
Yeah, so we'll be we're actually giving away a few later today.
You can win one.
Yeah.
Lucky.
But we'll